Okay, so we're told that we've got two connected masses. One we're given the mass, we're given the mass in terms of m, so 3m. The other one is km. We are told that k is less than 3. So that does mean that when we release this, q is going to move down and p is going to move up, because we were told that p definitely has a smaller mass than q. They're connected by a light inextensible string, so if it's an extensible, when it does start to move, they're going to move with the same acceleration because the string won't stretch at all. If it's light, it means the tension will be the same throughout the string, and it's a smooth pulley, so we don't need to worry about any friction where the two particles, where the string is moving over the pulley. It's initially held at rest with the string taut, and P and Q start off at the same height, so it looks like they do in the diagram, but we need to be clear about that. The system is released from rest, and yeah, so we knew that Q was going to descend because Q is the heavier particle, but we're also then given the acceleration, and we need to calculate the tension in the string. Okay, so start off with a diagram of the whole setup. So I've got my two particles. So there's P and there's Q. The weight of P is going to be kmg. The weight of Q is going to be 3mg. I know that Q is going to move down, which must mean that P moves up, and the tension will be the same in each of them, and it tells me that Q is moving down with an acceleration of 1/3 g. Okay, so because I don't know the mass of the value of k, it makes sense for me to look at Q to start with. So if I just sketch out Q, so Q has got the tension pulling it up, it's got its weight pulling it down, and overall what's happening is it's accelerating down with an acceleration of 1/3 g. And I am trying to find the tension. Okay, so if I use F equals ma, the downward force, the resultant downward force is 3mg minus t, which is the mass of, so this is Q we're looking at, so the mass of Q is 3m, and the acceleration, I'm told, is 1/3 g. So that's going to be 3mg minus t, so the 3 times 1/3 I'm going to cancel. So if I minus mg from 3mg, I get 2mg, and if I add the tension over, or add t over, I get that the tension is 2mg. That's going to be newtons because it's a force. If you did that and it didn't say to leave it in terms of g, so if you put 19.6 m, that would be absolutely fine as well if you actually used g as 9.8. Okay, right. So show that k is 1.5. Okay, so we're gonna know if we've got this one correct, which is a bonus. And it's worth 3 marks, so about the same amount of work as part A we're expecting. And obviously, if they're talking about a value of k, I'm going to need to start looking at particle P. So let's draw a diagram for particle P. So P has got tension up, its weight down. P is going to be moving upwards, and because the string is inextensible, however, with whatever acceleration Q is moving down, P must be moving up with the same acceleration. So if I use F equals ma for particle P, and I'll take up as positive because it's moving up. So if I'm taking up as positive, T minus kmg is its mass, which is km, times its acceleration, which is 1/3 g. And the other thing I know is that the tension is the same. So again, because of that assumption they told us that the string was light, means those values of t will be the same. So I can use this answer and say that the tension in the string is 2mg. So 2mg minus kmg is 1/3 kmg. So I can do a little bit of cancelling to make that look a little bit nicer. So they all have an m, and they all have a G. So that just leaves me with 2 minus K is a third K. So 1/3 K plus K is 4/3 K. So K is 2 divided by 4/3. And don't forget, this is a show that question, so I would just go a little bit overboard on showing my working. So 2 divided by 4/3 is 2 multiplied by 3/4. So that 1.5. And as this was a show that question, do just finish it off. So 1.5, which is what we were trying to show. Okay, so back to the question. So state how you have used the information that the pulley is smooth. So let's just be a bit lazy and just put up the answer for that one. So if it's smooth, we said at the start there's no friction, so that means there's no other forces sort of working on the rope. So we've used that when we used the fact that the tension was the same. Okay, right, and then I think there's more